it's through the analysis of these equations that we're going to find the tension. So let's think about the forces in the x direction. What are they? Because whatever they are, they're going to add up to 0. And what are the forces in the vertical direction and the y direction? Whatever they are, they're going to add up to 0. Let's consider the y direction. Forces on this object in the y direction, I see W, the weight, and I see the direction, it's downward. Let's put down a coordinate system here. There's x, there's y. So the vertical is y, the horizontal is x. And so what other forces are in the vertical direction? I see tensions, but they pull at an angle. They're pulling vertically and they're pulling horizontally at the same time. So if I want to know how this tension is pulling vertically, I'm going to analyze its contributions or its component upwards, and I'm going to consider its component sideways. Again, I draw these components parallel to my coordinate system, and then I can label them. My vector is always a hypotenuse. Its components are always parallel to my coordinate system, and I establish that this is the contribution of the tensions on an angle. It has some contribution horizontally and some contribution vertically, and I can label that. I can say, look, this tension pulling on an angle pulls up, which I'm going to label tension in the y direction. It also pulls to the side, which I label tension in the x direction. So the force in the vertical direction is the weight pulling down, and that's being balanced, because it's not accelerating, it's being balanced by part of the tension that's pulling up. And this tension, these two tensions are basically mirror images of each other, so I'm not going to analyze this tension. I'm just going to say it will also have an equal tug upwards as the wire on the left as the wire on the right. So there's two of those. Two tugs upwards, one by the wire on the right, one by the wire on the left. They're both pulling upwards. They'll both have similar looking. Now, I know that's equal to 0. And I know what the weight is. So if I bring the weight over to the left side, I can see that that's equal to 2 times two tensions in the vertical direction. If I divide by 1/2, I know what this vertical tension is. But the question doesn't ask what Ty is, it asks what T is. But so can I take the information in the vertical direction and basically move that over and tell me what T is? I could if I knew more information about this triangle. For example, if I knew this angle here, I'm going to call it alpha. If I knew alpha, or, hey, look, there's theta. People who know geometry, these are interior angles on the same side. That angle's theta. So that's even better. So if I know theta, I can use geometry. But what is theta? We haven't answered it. I can use the background geometry of the whole makeup. The background geometry is that the wire is length L, that it also has a height that I know. So I can find theta from the geometry of the situation. I could use this h is opposite, this height is opposite, this is the hypotenuse, I could use sine theta is equal to h over L to find theta. So now let's assume you guys can do this, you know theta now. Well, just for everyone who's needs a little help there, theta is equal to arc sine h over L, and on your calculators that's often with that symbol. It's basically the second function of sine. Alright, so now we know theta, and now we can use the similar geometry of our vector triangle to find out what that ty is. Or no, to find out what t is. T, if I put it here, is the hypotenuse. And ty is that one component. That is opposite of theta, and that's the hypotenuse. So I could also write, to find the tension, I could write sine theta is equal to ty over t. I know what ty is, I know what my theta is, I can solve for t.